This is the fifth and last video on section 5.3 partial derivatives. And so we talked about the second order partial derivatives in the previous video. And so here we're going to calculate some second order partial derivatives. So we start with f of xy. This is a polynomial of two variables, x cubed y squared plus xy cubed plus xy plus x. We start by calculating the partial derivative with respect to x, which is 3x squared plus y cubed plus y plus 1. Then we calculate the partial derivative with respect to y. Again, we're considering y a variable and we pretend x is a constant. So we have 2x cubed y plus 3xy squared plus x plus 0. That's the partial derivative with respect to y. Then f sub xx is a partial derivative with respect to x of the partial derivative with respect to x. Partial derivative with respect to x of these three terms is 0, so we simply have 6xy squared. F sub xy is a partial derivative of y. It's the partial derivative with respect to y of the partial derivative with respect to x. So we start with f sub x and we take the partial derivative with respect to y. And so we start here, calculate the partial derivative with respect to y. We have 6x squared y plus 3y squared plus 1. Then we take the partial derivative with respect to x of the partial derivative with respect to y. And so we start with the partial derivative with respect to y, calculate the partial derivative with respect to x. So we have 6x squared y plus 3y squared plus 1. So we're taking the derivative, the partial derivative with respect to x, so we're treating y as a constant. Let's see. Now we have, the partial derivative with respect to x of the partial derivative with respect to y. So we start here and we take the derivative, partial derivative with respect to x. So we have 6x squared y plus 3y squared plus 1. Might have done that one twice. Then we have the partial derivative of y. The partial derivative of y of the partial derivative with respect to y. So we start with this function, calculate the partial derivative with respect to y. We have 2x cubed plus 6xy plus 0. And that's what we have here. And we'll look at example 143. fxy is xy cubed plus xy. Start with the partial derivative with respect to x. Again, we're pretending that y is a constant. So the partial derivative with respect to x is e to the y plus y. For the partial derivative with respect to y, we pretend x is a constant. So the derivative of e to the y is e to the y. So we just have a constant times an exponential function. So we just have our partial derivative with respect to y is just that constant times the exponential. And then the partial derivative with respect to y of xy is x. The partial derivative of x of the partial derivative with respect to x right here. So we take the partial derivative with respect to x. That's just 0 because we're considering y as a constant. For f sub xy, we start with the partial derivative with respect to x and calculate the partial derivative with respect to y, and that's just e to the y plus 1. For this one, we start with the partial derivative with respect to y, calculate the partial derivative with respect to x. So we start here, calculate the partial derivative with respect to x, and so this term is a constant. So we just have that constant. So x thinks this is a linear function, then the partial derivative with respect to x of 1 is simply 1. for f sub yx, start with the partial derivative with respect to y, then calculate the partial derivative with respect to x. Again, x thinks this is a constant. So this is just xe to the y, and let's see, this partial derivative here with respect to x is 1. So we just have e to the y plus 1. And finally, we'll calculate the partial derivative with respect to y of the partial derivative with respect to y. So this is the f sub yy. We start here, we calculate the partial derivative with respect to y. And so y thinks x is a constant. So this is just a constant times an exponential. Its partial derivative is the constant times that exponential. Partial derivative with respect to y of x is 0. You're going to notice something, I think. These two partial derivatives were equal in this example. Also, our two partial derivatives here, these are called the mixed partials. Our two mixed partials here were equal in this example. So, that leads us to the question, are these two partial derivatives always the same? And the answer is no, but Clairaut's theorem says they're equal a lot of the time. So theorem 144 is Clairaut's theorem. Clairaut's theorem gives us the circumstances, I'll let you read it in your notes, but it gives us the conditions under which these two partial derivatives here are always the same. And those circumstances exist in pretty much all of the functions we look at. So I'm not going to claim that these two derivatives here, these partial order derivatives, are always the same, but I'm going to give you this piece of advice. If you're calculating these partial derivatives and these two things are different, go back and double check your answer, okay? Because chances are you've made a mistake. I'm not saying these things are always the same, but I'm saying for the functions we look at, they are most likely going to be the same. So if they're not, you should double check that.